second free response question was a circuit question. Again, a lot of times it'll be an electric field voltage Gauss's law problem, so electrostatics. The second question a lot of times will be electric circuits. The third question a lot of times is going to be something with magnetism, especially induced EMF or Ampere's law. It's not always true, but often that's the format, and this year was no different. So in this one we have a circuit, but it wasn't just a circuit that has resistors like we've always drawn. This actually shows a physical object as the resistor. So we have this rectangular bar, they give you the length of the bar, and they give you the cross-sectional area of the bar. And it says, it gives you the resistivity also. And it says that electrons are the sole charge carriers in the bar, and the wires have a negligible resistance, and the switch in the circuit is closed at time t0. The fact that electrons are the sole charge carriers really doesn't come up until later parts when we start talking about the fact that we look at the magnetic force on electrons when we place this in a magnetic field. But right now, we're just going to worry about the circuit stuff. So part A, calculate the power delivered to the circuit by the battery. Well, power is current times the voltage. And the voltage across that battery is going to be 9 volts. To calculate what the current is, we need to calculate the resistance. The resistance of a solid object of known resistivity is the resistivity times the length over the area. That is a relationship that you need to know. It's something that comes up in the multiple choice part of the AP test also. You at least need to know that it's proportional to L and inversely proportional to A. So the longer the wire is, the more resistance it's going to have. The fatter the wire is, the bigger the cross-sectional area is, the less resistance it's going to have. So for this, we have 4.5 times 10 to the negative 4 ohm meters times the length of 0.08 meters divided by the cross-sectional area of 5 times 10 to the negative 6 square meters. So if you calculate that, you get a resistance of 7.2 ohms. That means that the current is going to be 9 volts over 7.2 ohms, which is 1.25 amps. So then calculating the power is 1.25 amps times 9 volts, which is 11.25 watts. In terms of a circuit, this is the simplest circuit you can have. One battery, one resistor. The thing that makes this a little bit more challenging is they're not asking you to calculate current, they're asking for power. And you have to find the resistivity. So this is a question that if they actually put it on the AP test, you should actually be thanking them, because this is a very straightforward, fairly easy question, at least for the first couple parts. They throw in some trickier stuff later, but this first part you should get no problem. If you don't, you need to go back and look at this, because it should be something that by the time you take the AP test, you should be able to answer a question like this without any difficulties. Part B. On the diagram below, indicate the direction of the electric field inside the bar. And so point A is at a higher voltage, point B is at a lower voltage. If we move with the electric field, the voltage gets smaller. So that would mean that the electric field points to the right. Another justification is the current is flowing from A to B, and the conventional current flows from A to B. Conventional current is the flow of positive charge, and so positive charge moves with the electric field. It's going to feel a force in the direction of the electric field. It's that electric field that actually pushes those charges through the circuit. Now some people might say, well, but it says that electrons move. Okay, that's fine. So the electrons go the opposite of conventional current. So in the circuit, the electrons would have been going around counterclockwise. So that means that the electrons are going from B to A. Well, an electron, which is a negative charge, feels a force in the direction opposite the electric field. So if this electric field is pushing the electrons along, then that means that the electric field needs to point opposite the direction the electrons move. Part C. Calculate the strength of the electric field inside the bar. Well, the electric field is constant. And so we have that the voltage difference between the two ends is the electric field times the distance. Again, where that comes from is that the change in voltage is the absolute value of the change in voltage is the integral of E dot dr. And the electric field was constant, and so it just becomes E times D. So looking at this, we know that the voltage is 9 volts. We're looking for the electric field. We know that the length was 0.08 meters. So 9 volts divided by 0.08 meters gives an electric field that's 112.5 newtons per coulomb, or volts per meter. The way I set it up, I would have volts per meter, but electric field is also measured in newtons per coulomb. Again, they do also give you on the AP formula sheet that the electric field is the resistivity times the current density. So again, if you look at the equations that are on there and you know that you could use that one, they gave you the resistivity here. This current density is the current divided by the cross-sectional area. So that was the current of 1.25 amps divided by the cross-sectional area of 5 times 10 to the negative 6 square meters. So this electric field, and it would have been the resistivity of 4.5 times 10 to the negative 4 times 1.25 over 5 times 10 to the negative 6. And if you do that, again, you should get the same answer of 112.5. And you do. Either one is an acceptable way of doing this. A uniform magnetic field of magnitude 0.25 Tesla is perpendicular to the bar and is added to the region around the bar as shown below. Calculate the magnetic force on the bar. Again, if you have a current carrying wire, or in this case a current carrying bar, and it's in a magnetic field, then the magnetic force is ILB sine theta. And in this case, the angle between the direction the current is flowing and the magnetic field is 90 degrees. So this is just ILB. So we just In part A, calculated that the current is 1.25 amps. The length is 0.08 meters. And the magnetic field is 0.25 Tesla. So that magnetic force is 0.025 newtons. This is something that's a little bit different than some of the circuit problems they give it. This is something where half of this problem is going to involve magnetism. And that's not an uncommon thing. A lot of times in the second question, they will have some part of something that involves magnetic forces, magnetism, um, some of the induced EMF stuff. Sometimes the circuit questions get tied together with calculating things with Faraday's law, and that's what we're going to have in question 3. There's a little bit of circuit stuff that's involved there with resistance and resistors in series and calculating current that flows and looking at power. So there's usually about a full question that's dealing with circuit ideas. If there's not, then there's a lot of circuit stuff on the multiple choice part to balance it out. For this one, because they're going to ask some circuit things or circuit type ideas in the third free response question, they put in some other magnetism stuff here. We did lots of these problems with the force on a current carrying wire. This is the simplest force on a current carrying wire that you can have, where it's just ILB, where there's no angle, where the angle is 90 degrees, so you don't have to do the sine of any angle. It's just recognizing that you can calculate that current and that you know all of the other things. The electrons moving through the bar are initially deflected by the external magnetic field. So the fact that these are electrons that are moving they're negative charges, so that's going to be extremely important for this question. The electrons moving through the bar are initially deflected by the external magnetic field. On the diagram below, indicate the direction of the additional electric field that is created in the bar by the deflected electrons. So if we have this magnetic field that's pointing into the paper, there's a couple of ways of answering this. One of them is to say, okay, if I have electrons and they're moving opposite the direction of the current, from the right-hand rule, if I point my fingers in the direction of V to the left, and then I bend my fingers of my right hand to point into the board in the direction of B, my thumb is pointing down. So that means that the force on a positive charge would be downward. But we have a negative charge. So the force on a negative charge has to be in the opposite direction. So this negative charge is going to get pushed up to the top. So I'm going to get negative charges that build up at the top. So that means that the bottom of this is positive relative to that top. That's going to cause an electric field that points upwards. So in my answer here, this is going to be upwards. The other way of answering that was recognizing that at first those electrons are going to be deflected upwards, and so then some negative charge is going to build up along the top. But now those negative charges that are there are going to start repelling other electrons. But they're not going to repel them downward. They're going to push on them just hard enough so that the electrons are going to move through undeflected. So these electrons eventually experience no deflection and move through the bar undeflected. And so that means, and we're going to have this in part F, that the magnetic force is going to have to equal the electric force. the magnetic force was upwards. Again, that's what we just looked at. If the electron is starting at point B and is moving to the left, I take the fingers of my right hand and I point to the left, and then I bend the fingers of my right hand to point into the board in the direction of the magnetic field. My thumb points down, but it's a negative charge, so that magnetic force is upwards. And so that means that the electric force needs to be downwards. But again, it's a negative charge. And so if you want the electric force to be downward, a negative charge feels a force in the direction opposite the electric field. So if I need my electric force to be down to balance out the upward magnetic force, then I actually need an upward electric field. The upward electric field pushes the electrons downward. Again, it's extremely important that you understand how to deal with negative charges. The problems are much simpler with positive charges. But with this, they ask a lot of questions about the direction of forces on negative charges when they move in a magnetic field. So they ask you to use the right-hand rule, but then switch it. They ask you a lot of questions about the force on an electron in an electric field. Again, electrons are negative, so a negative charge feels a force opposite the electric field. The definition of the direction of electric field is the direction that the force would be on a positive charge. Part F, the electrons eventually experience no deflection, and they move through at an average speed of 3.5 times 10 to the negative 3 meters per second. Find the strength of the additional electric field indicated in part E. So this is not the electric field that we had before. That's still acting. This is just this additional electric field. So again, they're going to be deflected until the magnetic force equals the electric force. The magnetic force, a couple steps ago, we said that it was ILB. That was when we were looking at the current flowing. Here, we're now looking at the individual electrons that are flowing. So the magnetic force equation for individual electrons is QVB. Again, it's QVB sine theta, but these are moving in a straight line perpendicular to the magnetic field, so it's just QVB. And the electric force is Q times the electric field. So my charge divides out, although I could look at the front page of the formula sheet. The charge of an electron is given there, so you could put it in there and then divide it out. But this says that the electric field is the speed of the electrons times the magnetic field. They just gave us the speed, 3.5 times 10 to the negative 3 meters per second. And the magnetic field was 0.25 Tesla. And so the electric field is 3.5 times 10 to the negative 3 times 0.25. So this electric field is 8.75 times 10 to the negative 4. Again, volts per meter. It could be Tesla meter per second. All of those are going to be acceptable things. So volts per meter, newtons per coulomb, Tesla meters per second, they're all the same thing. So going over the scoring guidelines, part A was worth 3 points. It was 1 point for correctly substituting in the given values into the equation for resistance, rho L over A. just writing down R equals rho L over A got you no credit. You had to recognize that they gave you the resistivity, they gave you the length, and they gave you the area, and you had to put them in the correct spot. If you did 4.5 times 10 to the negative 4 times 5 times 10 to the negative 6 divided by 0.08, if you did rho A over L, then you didn't understand what those values were that they gave you, or you didn't understand the equation that was on the formula sheet, but you needed to go through and at least plug them in. Even if you didn't put down that it was 7.2 ohms, you at least needed to show the values correctly substituted in for one of the points. And then it was 1 point for correctly combining V equals IR and P equals IV to get an expression for power in terms of voltage and resistance. That was one way of doing it. That wasn't the way that we did it. We knew the voltage and we knew the resistance, so we calculated the current. But for this, you could combine those equations to get power is voltage squared over resistance. So that was a point to rearrange those equations. And then you plug in the values, and it was 1 point for the correct answer. Again, if you notice, they used significant figures here. There were 2 significant figures, so they rounded things off to 11 watts. We used all the decimals, so we had 11.25 watts. On the AP test, they say just use 2 or 3 decimal places, so either one would be acceptable. An alternate solution would be, again, correctly calculating the resistance, so plugging in the values. They say for correctly combining V equals IR and P equals IV to get an expression for power in terms of current and resistance. So we know the resistance and we know what the power, or we know what the current is, so we can calculate that. So it was 1 point for doing that, and then 1 point for the correct answer. Again, that's not the way that we did it. We did current times voltage. And so for that, it would have been 1 point for correctly calculating the current, and then 1 point for plugging it in and getting the correct answer. There's multiple ways of doing it. They're all equivalent to each other. They're all the same equation. Okay, part B, the electric field in the bar. It was 1 point for drawing an arrow pointing from A to B. Explanation or not, if you had that down, that was 1 point. It was 1 point for correctly indicating that the current is from A to B. So the conventional current, the flow of positive charge, goes from A to B, or the electron current is the opposite of the conventional current. So that would be going around counterclockwise from B to A. And then it was 1 point for correctly indicating that the electric field is in the same direction as the conventional current, or in the opposite direction of the electron current. Again, a way that you would say that is, what I said before. The current is flowing around the circuit, the conventional current, and if you just say current, it's implied that it's conventional current. The conventional current is flowing around the circuit clockwise. So that means that the positive charges go from A to B. And the conventional current is the flow of positive charge. The electric field points in the direction of the force on positive charges, so it must be from A to B. That would be a way of saying that, getting those 2 points for the explanation. Or you could explain it in terms of voltage. For saying that A is at a higher voltage than B, based on the way it's connected to the battery, and then saying that the electric field points from a higher voltage to a lower voltage. That would be the other point. And it says, note that the third point can be earned for an incorrect field direction consistent with an incorrect current or an incorrect potential drop or voltage drop direction. So if you had your electric field backwards, and you said that it was backwards because you said that your conventional current was the opposite way, you wouldn't get any points for the arrow. You wouldn't get any points for saying the direction of the conventional current, but you could get one of the 3 points by saying, if you said that the current is going to the left and the electric field points in the same direction as the current, you would get 1 point there. You wouldn't get anything for the direction. You wouldn't get anything for, there would be nothing for these 2 parts, but you could get 1 out of the 3 points. You could get that final point because you would have gotten that correct. Your explanation was right. You tied everything together the correct way. You just had things backwards from the very beginning. So they did allow partial credit for that. Part C was just worth 2 points. Again, recognizing that the electric field was uniform, and so the electric field equation is V over L, or V equals E times L. Again, change in voltage equals E times D. Saying something like that was 1 point, and then going through and plugging in the values and calculating it was the other point. Again, they just used the two significant figures, so they rounded off to 112 or 110 volts. We had 112.5 volts per meter. The other way of doing it, again, I had said before, the resistivity times the current density. So it was 1 point. You didn't get a point for just writing that down. Again, that's given to you on the formula sheet. So you would have to correctly put in one of those values. So if you correctly calculate the current density, and then you correctly put in what the answer is. So just taking the resistivity that they give you and saying resistivity times J wouldn't be any credit. You needed to correctly calculate the current density and then get the correct answer. Part D, magnetic force on the bar. It was 1 point for saying that force is ILB. They did give full credit even if you didn't plug anything in. And then it was 1 point for substituting for the current. So in part A, we calculated the current. So as long as you plugged in whatever current you calculated in part A, even if it was wrong, you could get the full credit for this. If you did ILB and used that current and used the correct length, and you used the magnetic field that was given to get the 0.025 newtons, that was what you needed to do. Part E was showing that the electric field was up. So there was no explanation for that. You either got it or you didn't. You could have even just guessed on that and gotten credit, even if you didn't know why. And then part F, for calculating the electric field. The electric force is equal and opposite to the magnetic force. Saying something about that, that was 1 point. Plugging in the correct expressions for the electric and magnetic force, QE and QVB, that was another point. And then correctly substituting everything and getting your answer was the final point. And again, on this one, they did have 1 point for correct units. They don't do that all the time. They're almost never going to have that on more than one question, but often they'll have 1 point on one of the problems where it was a point for the correct units. Here they said correct units on at least 2 numerical answers. Sometimes they'll say correct units on at least 2 numerical answers and no incorrect units. Here, as long as you had them on 2 correct answers, whether or not you had others that were wrong, that would be okay. For some, if you have any one unit that's wrong, they will take off points. And sometimes it says for correct units on all numerical answers. So it's however they decided to do it that year. So you never know. So make sure that you include units on all of your answers. For this, they wrote it as volts per meter for this unit. But if you just went through and you left it as Tesla meter per second, that would be perfectly acceptable. Correct units, it doesn't have to be the fundamental units. It just has to be, a correct form of the units. And so the chief graders scoring guidelines or comments from this. The intent of the question was to assess an understanding of simple circuits containing a bar-shaped resistor with certain properties, knowing the electric field inside the resistor, and the consequences of a magnetic field, an external magnetic field. How well did students perform? The average score was 8.06 out of 15. Again, you see that was definitely higher than we had before. 8.06 out of 15. Before we had like 6 out of 15. That means not necessarily that it's an easier question. That means that people understood this better, that they found it to be easier. About 25% of students earned scores of 12 or higher, so that's pretty good. A quarter of students got the majority of the credit. And about 18% of students earned scores of 3 or below. Again, your goal is usually to aim for an average of 7 out of 10 points. And so on this one, you should have been able to get at least 7 points, but you should have been able to get at least 8 points. Again, if you understood most of these things well, if you understood a lot of the ideas about circuits, you should be able to get 8 to 10 points, if not almost the full 15. But if you can get 8 to 10 on this question, that helps balance out another couple of questions. And if you can average 7 points per question, again, you're on your way to at least getting, mid-range to high 3, as long as you do decent on the multiple choice section. If you can get even better than that, if you can get 8 or 9 points, you're well on your way to a mid to high 4, if not a 5. The common student errors or omissions. Part A, many students did not correctly calculate the bar's resistance. But they say, even though the equation for the resistance is on the equation sheet. So you need to know those equations. You need to know what they mean, what they apply to. However, many other students were able to correctly solve for power dissipated in the resistor, as well as the force on the resistor due to the added external magnetic field. In part B, students found it difficult to determine and explain the direction of the electric field inside the resistor. Many students either got the direction wrong or else simply stated that the direction of the conventional current without addressing how the direction of the current was related to the direction of the electric field. So if you said that the electric field pointed to the right because the current went that way, that wouldn't give you full credit. That would give you 2 out of the 3 points. But you needed specifically to say the current is flowing that way and the electric field points in the direction of the force on the positive charge. So you needed to specifically address how the direction of the current was related to the direction of the electric field. That the electric field is what pushed the charges through the circuit. In part E, many students incorrectly stated that the direction of the additional electric field resulting from the imposition of the external magnetic field, which led to mistakes in solving for the electric field. What you saw from student scores, what's the message that you would like to send to teachers and their students to improve their performance on the exam on questions like this. Describe and emphasize the connection between macroscopic circuit variables and the average motion of individual charge carriers. So you need to understand how to do circuits, but you should understand how to do them when the resistors are not just the squiggly line resistors, just the ideal resistors, but we have a block of material. And you should understand what's going on inside that block of material, that you actually have charge carriers that are moving along, and those charge carriers feel forces. Those charge carriers are pushed by electric fields, and that if there's a magnetic field there, yes, there's a magnetic field on a current carrying wire, but we came up with that. We came up with ILB from using QVB. The current was charge per time. Velocity is meters per second. So QV is the same, if you look at the units, QV is coulomb times meters per second. If you look at IL, it's coulombs per second times meters, so it's coulomb meters per second. QV and IL are the same thing. If you have 10 coulombs flowing past a point every second, if you look at 5 meters of that wire, you have a certain amount of charge that's in that 5 meters. So the IL has to do with the charge and how fast that charge is moving. Again, you definitely want to go through and study electric circuits. You want to be able to do a lot of the regular circuits and RC circuits and circuits with inductors, because those are often the second free response question. But a question like this is a way that they can ask some of those same ideas. They really make the circuit analysis part of it simpler, but they bring in extra stuff. Again, a question like this should be one that after you've reviewed, you should be able to get easily half of the credit, if not more. And if you can't, you need to go back and look at all those things a little bit more. Really look at all of those details.